Okay, in this problem, we're looking at work done by a few different forces and at different angles relative to the object that is having the work done on it, which is a piano. So a person here is pushing a piano at 365 kilogram piano at an angle of 14 degrees above a slope. And the slope has its own angle of 24 degrees. The friction coefficient is given. That's the friction coefficient between the piano and the slope. And we're told that the piano will accelerate down the incline instead of maintaining constant velocity. So one thing here is that a value should be given rather than just referring to a previous problem. So it was an oversight on my part. But we do need a particular value that's referred to here, the pushing value. So the pushing force from our person, and that was calculated in a previous example, was or is 1,440 newtons. So quite a strong push. And that's actually how much pushing force is being provided. Okay, and in the previous example, that was actually enough pushing force for the same piano at the same slope and the same friction coefficient to maintain constant velocity. So if you want to check that for yourself, you can actually see that that's the required force to keep the piano from accelerating. What's different with this problem, and the reason that we were told up front that we should expect acceleration for the piano downhill, is that the pushing force is no longer provided parallel to the slope. Instead, the pushing force is pushed on the piano at an angle that's slightly above the slope. This means that the piano is going to have less normal force. If there's less normal force, there's less friction force, and therefore there's a greater effective gravitational force because friction isn't doing its part to counteract that gravitational force. Therefore, the pushing force is not sufficient to keep the piano from accelerating. And then we're told that the piano is going to slide for 2.5 meters, during which point it will accelerate. And we're asked for how much work is done by the man. That's the work done by the pushing force. How much work is done by friction, and how much work is done by gravity. And then we're finally asked for the net work done on the piano, and what is the final velocity of the piano, which we can find once we use the work energy principle with that net work. Now, the net work will not be zero because there's going to be an acceleration, which means we're going to have a different velocity than we started with, and which is zero, right? Because here we're saying that the system started from rest. Okay, so the first thing we want to do in this problem is draw all the forces and the appropriate angles for those forces. Okay, so here I have gone ahead and put those forces in. All right, and we can see all those values. All right, oh, let me clear this up got a bit messy. Okay, so cleaning it up so we can see that information. We have all the different vectors acting on our piano here. So we got the gravitational vector, we've got the friction vector here, we have the normal force vector, the pushing force vector. All right, the displacement is also shown because that angle is going to be important relative to all of those forces if we want to calculate work. All right, and you see there's a lot of angles going on here in the figure. And the green angles will actually come up once we start talking about the work, so I'll get to them, but I wanted to have them up front in the figure. The two blue angles are the angles that we were given. This is the angle for phi, which is the angle that the pushing force is provided relative to the slope, and here is the angle of the slope, which is relative to the horizontal. And those are 24 degrees for the slope angle and 14 degrees for the pushing angle. Okay, so we want to just rush in and find the works. The work of gravity, the work of friction, the work of pushing. However, we need to consider the forces, particularly before considering the work of friction, because we really don't know the magnitude of friction force. So we have to consider our free body diagram and our forces in x and y in order to do that. All right, and this is our chosen axis here. We're going to go with a tilted axis system so that just to make our lives a little bit easier in terms of components. Okay, so let's go ahead and do that, and let's take a look at the forces in x and y. All right, so we got F net in x and F net in y. Okay, so let's see what we're looking at here. Okay, so what's going on in x? Okay, well, in the x direction, we're going to have the a component of the gravitational force in the positive x direction, so it's Fgx, and then we're going to have the friction force in the negative x direction, so force of friction, and then we also have the pushing force in the negative x direction. And this is just because we define positive x as downhill. So we're going to have a component of the pushing force, which is going to be Fpx. Okay, and then I've just set the motion in x equal to ma. And that's a good reason, justification for having positive x point downhill is that our acceleration is positive. That's actually the direction of motion. Okay, and so again, this is primarily for the purpose of finding the force of friction. But let's, which means we're going to have to consider the normal force. So let's look at what's going on in the y direction. Well, in the y direction, we've got the normal force pointing up, and then we've got a component of the pushing force also pointing up. That's Fpy. And then we have a component of the gravitational force pointing down, which is Fgy. Okay, and this is going to sum to 0. Okay, that being a g there. All right, so now let's go ahead and solve for our normal force, because we have that the force of friction, so the force of friction, by definition, is going to be mu k because that's our given friction coefficient, and this is a kinetic situation. It's not a static situation. And by definition, it's mu k Fn. Okay, and then we need to find mu Fn. Okay, well, from our sum of forces in y, we have that Fn is just going to be Fgy minus Fpy. Okay, so then mu k is positive Fgy, okay, and minus Fpy. Okay, and what do those look like, right? So if we actually go and expand those terms, we're going to have our friction coefficient, so mu k, and then we're going to be multiplying by the y component. Okay, well, let's think about this. Okay, well, the y component of gravity, that's this one over here, is going to be cosine of phi. Okay, we know it's cosine of phi because this angle right here is phi, and we can find that with geometry or just thinking about kind of our limiting cases of what happens as phi approaches 0 or 90 degrees. Okay, so that's going to be mg cosine of, oh, and I said phi, I meant to say theta, excuse me on that. Okay, and then minus, well, now we need the vertical component of the pushing force. Okay, because that's decreasing the normal force, right? Because the pushing force is going up, right? So we need this component of that force. Okay, well, that's going to be the sine component. So that's going to be Fp sine theta. Okay, all right, and now let's put that in to find, so then to find the friction force. Okay, so actually we're in good shape to find the friction force. Excellent. Okay, so now we can move forward to think about the work. Okay, now of course, I mean, it ultimately, I mean, the questions were asked besides the work questions, the questions were asked in D and E, or particularly E. What is the final velocity of the piano? Well, I mean, we wouldn't have to use work. We could just go and find the acceleration, take our given displacement, and use kinematics to find the final velocity. But we're not going to do that approach here. We're going to use the work kinetic energy approach to find the final velocity. Okay, so let's consider our work. Okay, so we have 4 potential works because we have 4 forces. So we got the work by the normal force. You can guess what that's going to be. The work by the friction force. Okay. Okay, so as I was saying, the work done by the friction force, the work done by the pushing force, and the work done by gravity. Okay, well, the work done by the normal force, well, let's, we can think about it, right? We know what the normal force is. It's Fgy minus Fpy. So, I'll even write that just to be thorough. Okay, so it's going to be mg cosine of theta minus Fp, right? Which is a given. We know that magnitude. Cosine of theta. Actually, this is actually sine of phi. So I wrote that incorrectly in the previous step as well, right? Because that's not the angle of the slope, but rather the angle of the pushing force. All right, so we got to fix that there. All right, and then that would be multiplied by the displacement, and then the angle between the two. Well, what's the angle between the normal force right here and the displacement vector? 90 degrees. Okay, so then we just got a cosine of 90 degrees. Okay, and cosine of 90 is 0, so we just get 0 joules for our work by the normal force. Okay, all right. Well, for the work done by friction, we've got the magnitude of the friction force, which we already went through the work of doing as a recent previous step. So a lot like the normal force, except just with the mu k. Okay, so mg cosine theta, that one actually is theta. And then fp sine of phi. Okay, and then that's going to be multiplied by cosine of the angle between the two, which I have here as theta f. Okay, because the work of friction is exactly anti-parallel to the displacement, so it's 180 degrees. Okay, so that's just, that one is just going to be 180. Okay, so the next one for the pushing force. Okay, what we got for the pushing force? Okay, so for this one, and actually I realize here this should be called phi p, not phi d, because it's supposed to be the pushing force angle. All right, but let's get back to it. So the pushing force, that was just given. All right, so that's just fp, right? Given magnitude, that is. And then we have the displacement, which I forgot over here, right? Because without meters, it's not work. Right, so that's d. All right, so here, multiply by d as well. And then we got the angle between the two. Okay, well, that's going to be cosine of phi p. Okay, well, what is phi p? Well, what it is 180 degrees minus 14 degrees. Okay, so we can write that here. Phi p, so the angle of the pushing force relative to the displacement, right? So lots of angles here, is 180 minus 14. Okay, so that is definitely one of the angles that we need. Okay, and then lastly, for the work of gravity, okay, which is not 90 degrees to the displacement, right? Because this is not a flat surface. So gravity, we can clearly see that the angle between the displacement and gravity is definitely not 90, and we call it here phi g, and we'll see what it is. Okay, so we're going to have mg, which is the gravitational force, and we'll be multiplying by the displacement, and then cosine of phi g. And what is that angle? Well, we see in a similar manner to the way that we found the angle of the pushing force, that the angle of the gravitational force relative to the displacement is 90 minus 24. All right, it's going to give us 66. Okay, so let's make those calculations, and we'll just write our values over here. All right, so I'm just going to plug them into the calculator so you can see the values. Okay, so if we take a look at the first one, the work of friction. All right, so that one is going to be, all right, so let's see how much we can get here so we can see the values. Okay, zoom in a bit. There we go. All right, so it's going to be 0.38 and then multiplied, okay, by, 365. All right, and then times 9.8. Turn that mass into a weight. Okay, and then we've got cosine, and then 24 degrees. Okay, 24. Okay, close those, and then subtract the pushing force that we solved for. So that's our 1440. And then that's going to be multiplied by sine of phi. All right, so sine of 14 degrees. Okay, and close those, and close it again. Okay, and then we're going to go up mode. We want to be in degree mode. Okay, so let's get that number. Okay, so here we calculated 1,110 joules. All right, double check our equation. Okay, yep, correct parentheses, correct angle there on the sign. All right, looks like it all checks out. Looks good, and nothing was forgotten. Okay. All right, so let's do the same thing for the simpler work calculations. That would be the work of pushing and the work of gravity. All right, so for pushing, we'll start with that 1440 again. Okay, and then we're just going to multiply by, oh, I did leave off the displacement on the last one. Yep, I knew something was missing. So let's go ahead and actually clear this real fast. So just, and I want to take this value and actually multiply it by 2.5, right? Because I left off that 2.5 meters for the actual displacement. Okay, so times 2.5. There we go. There's our joules. 2,773, or rounding to 2,770. Okay. So 2,770. All right. All right. Looks good. Okay. So let's not make the mistake with the work done by pushing. So 1440 multiplied by 2.5 multiplied by cosine of that angle that we solved for the pushing force, which was 180 minus 14. All right, so let's do our cosine, and then 180 minus 14, close parentheses, get our value. Okay, so we have a negative value here, and then does that make sense? Well, yes it does, because the pushing force is opposing the displacement, so it will absolutely be contributing to a negative value. All right, so we got 3,350. That's joules. Okay, so that's the negative work done by pushing. All right, because most of it is opposite the direction of displacement. Only a small part of it is perpendicular, and thus creating no work, zero work. Okay, and so now let's look at the work done by gravity, and we'll do a similar thing here. And the nice thing about doing it all carefully with the angles here is that the negatives come out naturally. You know, yes, we could have just kind of thought about the component, say the x component of the pushing force, and said, well, that's the only one that's going to be non-zero, right? This component right here, and then just found its magnitude, and then thought of the angle as a second step. But we can all do it in one step. So times 9.8 and times 2.5. Not to make that mistake again, forgetting the displacement. And then times cosine of phi g. So cosine of 90 minus 24. So 90 minus 24. All right. Close the parentheses, get our value. Okay. So then we've got, yep, that gravity is doing positive work. Okay. 3,640 joules of positive work. 600, sorry about that. Okay. 640 joules of work. All right. So yeah, the numbers are definitely making sense, because we've got these two large positive work values that they're sum up to, well over 5,000 joules. And whereas the negative work, the pushing force, is not really close to that value. And so what we're seeing is that the pushing forces isn't sufficient to overcome the other two forces, or the work created by the friction force and the gravitational force is outweighing the work created by the pushing force. All right. So then it asks for these values, right? So man, friction, gravity. Okay, so we can just actually label these A, B, and C, right? So for this one was A, The friction was B, right? So the order is all over the place, and then C was gravity. Okay. All right. And so then question D, what is the network? Well, that's straightforward enough at this step since we have them all. So net work is, of course, just the sum of these different work values. So it's just going to be the work of friction. I'm just going to leave out the normal work, or the work done by the normal force, because we know it's 0. Work P, work gravity. Okay. And so when we sum up those values, we can easily do that over here. So we're just going to take this one. That's the work done by gravity. We will add that with the work done by the pushing force, and then add the work done by the friction force. Okay, so our net work is 3,060 joules. 3,060 joules. Okay, so I might as well put some boxes around all our answers here. All right, and as well as our network stated here. And then we're asked for the velocity of the system. All right, so then we're going to use the work energy principle that says that the net work is equal to the change in kinetic energy, which is just going to be 1/2 mv final squared minus 1/2 mv initial squared. Now v initial is 0 because the system starts from rest. So then if we're solving for that final velocity, we're going to have that the final velocity is just going to be 2 multiplied by the net work divided by m, all inside the square root. All right. All right. And so what is that going to look like? Well, we're going to have 2 multiplied by 3060 joules, and all divided by 365 kilograms. All right. And unit-wise, if we think about it, joules are, kilogram meter squared per second squared. And so then if we divide by kilograms, the kilograms cancel. We got meter squared per second squared. And then when we take the square root of that, that just gives us meters per second. So the units of velocity. Okay. So it's good to make sure that the equation does check out dimensionally. All right. So let's get that value. So I'll set up the square root. And we'll get 2 multiplied by our value above, right? No intermediate rounding. And divided by 365. All right, looks good. All right, 4.09 meters per second. All right, picked up a lot of speed, decent amount of speed at least. Person was not able to stop it despite their, huge amount of pushing force with 1,400 newtons. Still sped up. It is a big piano. And they weren't effectively using their pushing force because they weren't pushing parallel to the surface. Now, of course, they could actually even more effectively use their pushing force if they were pushing into the surface, because then that could contribute to the friction force. Now, that is assuming a big enough friction coefficient to make the push worthwhile. And there's actually a little bit of optimization there. Okay, but I hope this problem was interesting, and thank you.